This is part 8 in a series of videos in which I'm attempting to repair an HP9830A desktop calculator. In the previous video I got as far as correcting a fault in the microcode controller where this IC had failed, and also we had an issue with a faulty ROM. This resolved a problem where it was stuck in a tight loop from reset, and it now seems to be, at least to a certain extent, processing the microcode steps as it should do. So the next step is to run it through some microcode and see if it's actually carrying out the instructions as it should do. So this is the microcode that in theory it should be running through. So we start at the top. This is the reset vector. So what I'll do is I'll boot up the HP, and we should boot into this instruction, and then we'll follow it through and see how far we get. Okay, so we've booted up. Hopefully you can see this on camera. We've booted up into FF, and the next instruction, as you can see, is FE, which is what it should be. So we've come to FF. I won't go through the meaning of each instruction unless there's a specific need to, but in essence we should now jump to FE, and that's exactly what we do. So we follow through the next instruction, FE, we should jump to A6, and again we jump to A6. From A6 we should jump to 89, which again you can see we do. So what it's doing here is going through an initial self-test. It's initializing some registers. I don't know if it's actually doing that or not. It's not checking, it's just doing these as kind of blind instructions. But we'll go through until we get to what appears to be an error, and if nothing shows up we can start examining each of these steps to see if it's carrying these out correctly. So from 89 we should go to A1, and indeed we go to A1. So we know that the next address value must be correct because we're going through to the correct destination address. Then from A1 we should go to 4C. So A1, the destination address is 4C. Again we're going through to 4C. We should then go through to CA, which we do. We've got CA showing. And then the next one we should go to 57. And indeed we do go to 57. So on to the next page. And then from 57 we should go through to 55, which indeed we do. And then from 55 we should go to 9E, which we do. You'll see that some of these instructions are different lengths, and that's because, as I mentioned in the previous video, the instructions themselves contain information about how many clock cycles are required for each instruction, and they appear to be loading correctly. So it does look like the microcode unit is loading the instruction up to a certain point correctly. So we now get to 9E, and from 9E we're going to EB. However, if we look at the instruction we can see that we should actually be going to EA, and this is not a fault in the address location that's loaded within the instruction, because we do actually have the correct next instruction address value. So this is the first instruction where it's trying to make a decision. So it's deciding whether or not it needs to jump to EB or EA, and it's doing that based on the binary carry flag that's in the Q register, and this information is encoded into the instruction, of course. So this is the first instruction. Now the way it makes this jump, or this decision, if we look at the schematic, is this circuit down here that we had a problem with that's now working. If it needs to look at flags or status values within the system, then all those status values come in through these lines and they go into this 16 to 1 multiplexer, and this multiplexer lets us select which particular status line we want to look at. So in this case it's the BC line, which is this one. The BC line comes from the ALU, as you might expect, so it's a binary carry flag. So this is the ALU circuit and this is the binary carry flag. So the fact that we're not jumping to the address that we want to means that the fault could either be somewhere in the ALU or the loading of the ALU or register, or it could simply be that the multiplexer isn't working. This is the first jump instruction we've encountered since boot up, so we haven't actually seen if this works yet. So in terms of how it knows which input to select, if we go back to the microcode, we'll see that in the instruction we're currently looking at, which is the one at 9E, then the instruction includes information about which of these inputs to select, and it does that by way of the primary 4 bits of the next address. So that is the output from this ROM, which is part of the instruction. It's 4 bits of the instruction contain a value that not only determine the next basic address it wants to jump to, but also select which of the inputs are required to be examined if required by the current instruction. And if we look at the primary address for instruction 9E, then we can see that it is 7. So in other words, on these 4 bits we're getting a value of 7, and because this is a sort of simple one-to-one relationship between the address on here and the selected input, we should be selecting input D7. So input D7 is this one, and that is indeed the BC flag input. So in other words, for this instruction, the multiplexer is connecting BC through to its output, and then this circuit here can check the value of BC and determine whether or not to modify the destination address. In other words, it can use BC to determine or partly determine the destination address, and that allows it to jump. So if BC is in one state, it will jump to one address. If BC is in the other state, it will jump to a different address, and those 2 addresses are what are encoded into the instruction. So in this case, the 2 possible addresses are EB or EA. We want to jump to EA if the test is successful. It's jumping to EB, so the test is failing, but that might be because we have a fault in the ALU or the multiplexer. So next step is how to go about testing this. And the easiest way, of course, is we'll check the address, because it could be that the address is wrong, of course, or that BC itself is not being correctly set, or that there's still a fault in this circuit here. So what I've done is I've hooked up the logic analyzer so that we're now monitoring BC as well as the output of the multiplexer, and also we're monitoring these 4 bits directly on the multiplexer. So I have the 4 address lines that we were using that were calling data, and they are connected directly to the 4 selection lines or address lines of the multiplexer, and they are of course for instruction 9E. So if we now look at 9E, which is this instruction, we can see that data, which is the control input to the multiplexer, does indeed have a value of 7. So we know that the 4 bits going into the multiplexer that control the selected input it is indeed set to 7, so that's correct, and we have selected the correct input, which is BC. Okay, so I'm recording this video as I'm going along and finding the various faults, and I realised that the explanation into what was causing this incorrect jump was getting a bit convoluted and confusing. So what I've decided to do is just step back a bit and do a very quick explanation as to where the problem possibly lies. It turned out that the BC line, the binary carry line, is high and it should be low as a result of that test, but the reasons for that are possibly so complicated that the video would possibly not have made sense. So what I've done here is I've used the free version of DaveCAD to draw a hugely simplified version of the processor. Now, it's a serial processor, which means that most operations for loading and processing data in the registers are carried out in a serial fashion. That makes the overall circuitry more compact and less complicated, but it makes understanding the way that this system operates a little harder to explain. So I'll try and be as brief as I can with the explanation, and then we'll go back to what the possible causes of the fault could be. So firstly, we have our series of microcode ROMs. There are 7 of them, and they provide a 28-bit instruction. They are controlled, they're all on a common address bus, and they're controlled through a single register. So it's a single 8-bit register, and that determines the next microcode instruction to be carried out. Again, not to be confused with the main system code. The next address that will be carried out after the current one is determined partly by the current instruction, so the address is fed back. This is an address modifier, it's not the actual address that's required. That goes through some decision-making electronics. That allows the microcode system to make conditional jumps. The clock system consists of an 8 MHz master clock, and that is what we could consider to be the bit clock. And then the number of bits in each microcode is determined by a divider, and the division ratio is determined by part of the instruction. So one of the ROMs contains information about how many microcode bits, how many bit clocks there are in each microcode cycle. So I haven't shown all the logic that controls how this works, but essentially the number of bit clocks per instruction is just simply determined by the division ratio. The remaining bits of the instruction contain the control bits required to fulfill the actual requirements of the instruction. So for example, here we have the M register, the A register, B, T and Q registers. They're all 16-bit registers, and the way that they are loaded and read is in a serial form, and the instruction will contain information about which input is selected and also which output is selected. So for example, if you wanted to swap A and B, if there was an instruction for swapping A and B, then what you would do is you would select input A, output B, and then you would cycle the entire register through the accumulator, and that would effectively swap the two over. The ALU obviously, of course, provides mathematical functions in addition to just allowing it to be used as a shift register. And the results of those instructions can be some status bit information, such as binary carry, decimal carry. That status is fed back to the decision-making part of the microcode controller, and if the instruction requires that, for example, BC is checked as a conditional jump parameter, then this is what actually does that. And so this is the problem that we have with the system at the moment, is that BC is stuck high, and that's what's causing us to jump to the fail address when it's carrying out this particular self-test. Now, this is the reason I decided to draw this diagram, because the explanation as to what can be causing that was getting quite convoluted. But as you can see here, it essentially means that any part of the system other than the microcode generator itself could be responsible for failure of BC to be set to the right value. So for example, if there's a fault in one of these registers, or the selection devices, or the logic that controls the clocking to the individual registers, then that can give rise to the wrong value in BC, or indeed a fault in the ALU itself. So essentially anything other than what we've already looked at could cause BC to be incorrectly set. So what I'm going to be doing from this point on is just working my way through testing each of these registers and the selection circuits and the ALU in a logical manner based on what the microcode is doing, to try to figure out what's not working and why BC is being set when it should be clear. Okay, well, it's several days later, and I've been doing some testing on the unit, trying to figure out where the problems lie. Finally got the boards for the risers that I wanted to make, so I've been able to properly test the boards. What I actually did was make the boards all the same. They're all 25 conductor wide risers, and I'll just cut them down to whatever width I want and then make up a full set of risers. If you want to buy some of these, because I made plenty of spare ones, then they'll be available from here, and you might find them useful. They're 3.96mm pitch, or 0.156 inch pitch risers, so they're fairly common size. But having those makes it a lot easier, because obviously I can fully test the boards with them plugged in and powered up. So I've been working my way through all the CPU cards, including the T and the M register cards. I found a huge number of failed devices. I think there's about 30 devices I've had to change so far, and I'm just changing the last one on the microcode card, and hopefully after this I'll be able to power it back up and see if we're making any progress. I have been finding as I've gone through that each time I've replaced the faulty device, the code is getting further through, but the binary carry flag was still incorrectly set in some cases, so there were still issues with addressing some of the registers. The display is still blank, and I think that could well be this device. It's partly dry. It's one of the shift registers in the microcontroller card, and the 4 bits select the in-out channel that's used, and because it's faulty, then the system wasn't able to select the in-out channel, and that includes the keyboard and the display, so it wasn't able to actually address those cards at all, which is why there was no activity whatsoever on the display card. Okay, so I'll get this fitted and get back on camera and see if it's improving things at all. One other interesting point, you'll notice I now have the original ROM refitted. So while I have programmed one of the alternate devices and it works, I tried this one back in just out of interest, and it does seem to be working. So I think that possibly the device that I changed, which is this one that was faulty, that was the first device that I changed, was possibly making this device unable to drive its outputs properly. So I think the replacement device just has more drive, and it was able to overcome that problem, but this one couldn't. But now I put it back in, it's working fine, so I'm going to leave this one in. Notice it's in a socket, but I will have to take the socket out and put this directly onto the board again, simply because there isn't room between the cards to socket the chips, which is why I'm not putting sockets in for the devices I'm changing, which is something I would normally do. Okay, so I'll get this chip fitted, get back on camera, get the logic analyzer reconnected, and see where we are now. Okay, so I fitted a new IC, and what we'll do now is try to boot up the HP again and see if we get any further through the test routine. I have the analyzer set up to trigger on the same address as previously, which is FE. So I'll arm the analyzer and boot up the HP. And we've now captured some data. I'll scroll across and see if we've jumped to the fail address or the pass address. So if you recall, when we got to the decision part, which is here, we were jumping to EB and we should have been jumping to EA. EB is if the self-test fails, EA is when the self-test passes, and as you can see here, the self-test now passes. Now this is just a very basic self-test of the microcode controller. It doesn't really test much else, but it does require an awful lot of the electronics to be working to get to this point. Now from here on it does get much more complicated, because the next instruction following EA is to try and load instructions from the main ROM, and these instructions are of course system instructions. In other words, these are the code that the system runs as opposed to the code that's running in the microcode controller. I'll have a quick look at this and get back on camera and see how far the machine gets through this process. Okay, the display was blank. It still wasn't doing anything to try to access the display or send data to it. Although it's showing characters here, or just garbage actually, rather than characters. What I've done is force the in-out board to send keyboard data to the display. This is really just to see if the display is capable of doing anything at all. And I also wanted to see what activity was going on within the machine. Now I've done quite a bit of probing around, and there is quite a lot of activity in response to key presses. And in fact, if I press keys on the keyboard, I don't know if you can see that the display is changing in response to me doing that. It's showing garbage because it's sending the data to the wrong port. And that does seem to be the issue at the moment, is either the instructions cannot be properly decoded, so it can't send data to the correct port. In other words, it can't refresh the display correctly, which is why it's not scanning the display, it's just showing information in the first columns. Or there's an issue with the main ROM, and the information it's trying to get from the main ROM is garbage, and it's just not running correctly. I can't really see that being the case, because I wouldn't expect it to continue to run the way it is if it does that. Also, it doesn't come up in this mode every time I reboot it, so I think there's something a bit flaky going on still in the microcode controller. But either way, the fact that it's responding to key presses, and I see the data and the signals within the microcode controller starting to come to life, does tend to indicate that it is successfully reading something from memory and trying to execute it. Now of course, because of the nature of this machine, in that the microcode controller essentially runs the show as far as getting instructions and deciding what to do with them, it doesn't mean that the main ROM could be at fault, in which case the machine's probably not going to be repairable. It's very unlikely I'd be able to find replacements for them, and even if I could, the cost would be prohibitive for a machine like this. So I'll carry on poking around. That's it for this video, and in the next one hopefully I'll be able to make some progress on figuring out what's going on with the system. If anyone's ever worked on one of these or has any advice, then comments welcome.